In this lecture video, we are going to look at custom hypothesis tests in the context of a completely randomized design. Now, we've looked at how to perform the overall analysis of variance for the completely randomized design, and you'll recall that the ANOVA tests the null hypothesis that the treatment means are all equal against the alternative hypothesis that at least one of the treatment means is different than the others. Now, that's never going to be the end of our analysis. That's really just the starting point. If we determine that differences exist, then we're typically wanting to follow up and find out where those differences are, and to perhaps even make more complicated types of comparisons than pairwise comparisons. So with that in mind, suppose that we are interested in testing hypotheses about a linear combination of the treatment means. Again, the sum I going from 1 up to the number of treatments t of a sub I times mu sub I. So the a sub i's are the coefficients in this linear combination. If those coefficients sum up to 0, then the linear combination represents a contrast and is a comparison of some sort between the treatment means. Now let's first look at a two-tailed hypothesis test about a linear combination of treatment means. All right, and so the null hypothesis here is that the linear combination of the treatment means is equal to some hypothesized value, which we'll denote by lambda sub 0, against the alternative hypothesis that the linear combination of the treatment means is not equal to that value, lambda sub 0. We're going to perform the test at a significance level that is we'll denote by alpha. Now, based on what we've learned about the distribution, the sampling distribution of the estimate of the linear combination, we can come up with the test statistic that we'll use. And this version of the test statistic we're going to call t-calc, because the reference distribution for this test using this test statistic would be the t distribution itself. So in this case, the test statistic, t-calc, is given by the point estimate of the linear combination minus the hypothesized value of that linear combination divided by the estimated standard error of the estimate of the linear combination. We have given expressions for these estimates, the estimated linear combination itself and the estimated standard error of that estimate of the linear combination. We've given those formulas in a previous lecture video. Now, this is a two-tailed or two-sided test. The rejection criterion for this test is therefore a two-sided rejection region. In particular, we're going to reject the null hypothesis if our test statistic t-calc is either really small or if it's really big. And in particular, if t-calc is either less than the negative of the upper alpha over 2 percentage point of the t-distribution with a given number of degrees of freedom, or if t-calc is greater than the positive version of that critical point. And so this is the rejection criteria, and the number of degrees of freedom associated with the reference distribution is r dot minus t, which again is the number of error degrees of freedom from the ANOVA table. Now, an equivalent procedure for performing the two-tailed hypothesis test, and again for performing the two-tailed hypothesis test, is to use the squared version of that test statistic. All right, so notice here that if we square this, then that's what we're going to get in this expression here. And it turns out that that test statistic under the null hypothesis has an F distribution. And so we could call this t squared, t-calc squared, but we're going to call it f-calc just to remind ourselves that the reference distribution using this version of a test statistic is the F distribution itself. Okay, and so then the rejection criteria, if we're using this particular test statistic, is to reject the null hypothesis if the test statistic f-calc is greater than the upper alpha percentage point of the F distribution with numerator degrees of freedom equal to 1 and denominator degrees of freedom equal to r dot minus t, which is again, the number of degrees of freedom associated with the error line in the ANOVA table. Okay, next let's look at a left-tailed hypothesis test. In particular, the null hypothesis here is that the linear combination of the treatment means that we're interested in is greater than or equal to some specified value, lambda 0, versus the alternative hypothesis that says that that linear combination of the treatment means is less than this value, lambda 0. Again, we're going to denote the significance level of the test by alpha. The test statistic that we'll use here, again, is t-calc. It's the same test statistic that we looked at for the two-tailed test. All right. The difference here is that now we have a left-tailed rejection region. So the rejection rule for this left-tailed test is to reject the null hypothesis for small values of the test statistic. Specifically, the null hypothesis is rejected if our test statistic t-calc is less than negative t sub alpha, all right, where again t sub alpha is the upper alpha percentage point of the t distribution with degrees of freedom given by r dot minus t, and then we have to put a negative in front of that. All right, so that is the critical point. All right, so we reject the null hypothesis again if t-calc is less than negative t sub alpha here. And then finally, let's consider the right-tailed test. And so the null hypothesis here would be that the linear combination of the treatment means is less than or equal to lambda sub 0 against the alternative hypothesis that says that the linear combination of the treatment means is greater than lambda sub 0. We use the same test statistic, t-calc, all right, but because this is a right-tailed test, the rejection rule is to reject the null hypothesis if t-calc is greater than this critical point, the upper alpha percentage point of the t distribution with degrees of freedom equal to the number of error degrees of freedom in the ANOVA table. All right, so we've looked at a procedure for testing hypotheses about linear combinations of treatment means. These procedures can be used to perform the following. Hypothesis test about a single treatment mean, pairwise comparisons between treatment means, more generally, any single degree of freedom contrast involving two or more treatment means, and then finally, any hypothesis involving a linear combination of treatment means regardless of whether the linear combination is a contrast. So this is a very general framework within which we can now perform custom hypothesis tests once we've concluded from the ANOVA that differences exist among the means. If we conclude that, again, if we conclude that differences do exist among the means, then it makes sense to try to find out where those differences are. And that may involve performing pairwise comparisons, but it may also involve performing comparisons that are more complicated that are suggested by the form of the treatment structure. Those comparisons may involve contrasts of some sort or form, but again, the procedure that we're looking at here does not require that the linear combination constitute a contrast. It can be any linear combination that is relevant and makes sense in the context of a particular research study. All right, let's look at an example. This will be example 2.4. Consider again the experiment to compare rice varieties described and analyzed in example 2.2. The experimenter expected rice variety 4 to outperform the other three varieties. Their real interest is in determining to what extent variety 4 outperforms the others. Now let's suppose that the specific question to be answered is this: is there sufficient evidence at the 0.05 level of significance to conclude that the mean rice yield for variety 4 is more than 30 pounds per acre greater than the mean of the other 3 rice variety mean yields. Now remember that in setting up the hypotheses for a test, we always put what we're trying to show in the alternative hypothesis. And so in this case, what we would put in the alternative hypothesis is the statement that the mean rice yield for variety 4 is more than 30 pounds per acre greater than the mean of the other 3 rice variety mean yields. Expressed notationally, it would look like this. So again, we're looking at the alternative hypothesis for the moment. The alternative hypothesis here says that the arithmetic mean of the mean yields of varieties 1, 2, and 3 plus 30 is less than mu4. The other way to say that would be that the mean yield for variety 4 is more than 30 pounds per acre greater than the arithmetic mean or arithmetic average of the mean yields of varieties 1, 2, and 3. So that is why we have the alternative hypothesis expressed the way we have. The null hypothesis would therefore be the logical complement of that, and so it would be the statement that mu1 plus mu2 plus mu3 over 3 plus 30 is at least mu4. Now these hypotheses are expressed in canonical form in the following way, and what we're going to do here, I'm going to subtract mu4 from both sides and subtract 30 from both sides, all right, to get the parameters on one side and the constant on the other. And so the null hypothesis would be mu1 plus mu2 plus mu3 over 3 minus mu4 is at least negative 30. The alternative hypothesis would be mu1 plus mu2 plus mu3 over 3 minus mu4 is less than negative 30. Now obviously, each of those hypotheses could be expressed in the opposite direction by multiplying both sides of the inequalities by negative 1, and that would therefore flip the directions of the inequalities. That would be an equivalent way to do it. All right, now from the canonical representation as we have it here, the contrast coefficients are seen to be A1 equal to 1/3, A2 equal to 1/3, A3 equal to 1/3, and then A4 equal to negative 1. Now again, if we happen to express the hypotheses with the differences taken in the opposite direction, in other words, if we multiply both sides of each inequality by negative 1, then the signs of the contrast coefficients would need to be multiplied by negative 1 as well. Okay, so as we've got it expressed, this is a left-tailed test. And again, if we go back up here and look at the alternative hypothesis, we see that the inequality is pointing to the left. All right, so that clues us in that this is a left-tailed test. The rejection criterion is to reject the null hypothesis if the test statistic, t-calc, is less than negative t sub 12, 0.05. So that's the negative of the upper fifth percentage point of the t-distribution with 12 degrees of freedom. And that value turns out to be negative 1.782. All right, so the point estimate of the contrast is equal to the arithmetic average of the point estimates of the mean yields for varieties 1, 2, and 3, minus the point estimate of the mean yield for variety 4. And we see that that is equal to negative 166.083. All right, now in order to calculate the t-statistic, we need to divide this quantity. Well, what we'll do is we will subtract negative 30 from that, but what we need to do is we're going to need the estimated standard error of this point estimator. Again, the point estimator being negative 166.083, And we need the estimated standard error of that quantity. And if we go back and just take a quick look at the formula for the estimated variance and the estimated standard error of a linear combination of treatment means, we see that this is the formula for the estimated variance for this point estimate of the linear combination. All right, and you can see here that this estimated variance involves the contrast coefficients in terms of their squared values and also the sample sizes for each of the samples. All right, and then we take the square root of that, and that gives us the estimated standard error for that point estimate of the linear combination. Okay, and so this is the formula for the estimated standard error of the point estimator. All right, and we see that that's equal to 37.2215. Okay, so then the test statistic, t-calc, is equal to the difference between the estimate of the linear combination minus, and then lambda sub 0, where lambda sub 0 is the hypothesized value in the canonical form. If we go back up here, we see that that value is negative 30. All right, and so we subtract negative 30, and so the negatives become a positive, and so we have the point estimate, negative 166.083 plus 30. All right, so negative 30 or plus 30, and then we divide that by the estimated standard error of negative 166.083, and again, that estimated standard error, well, we found to be 37.2215. And so when we take that ratio, the test statistic t-calc is found to be negative 3.656. Now, since that value, negative 3.656, is less than negative 1.782, the rejection criteria has been satisfied, and so we would reject the null hypothesis. And so we would say that there is sufficient evidence at the 0.05 level of significance to conclude that the mean yield of rice variety 4 is more than 30 pounds per acre greater than the mean of the other 3 rice variety mean yields. Expressed notationally, there is sufficient evidence at the 0.05 level of significance to conclude that mu4 is greater than 30 more than the arithmetic average of the mean yields for varieties 1, 2, and 3. Now, it's usually not enough just to perform a hypothesis test. We're typically interested also in constructing a corresponding type of confidence interval. And in this situation, again, it's informative to construct the corresponding type of confidence interval to augment the results of this test. Now, in this case, a corresponding type of interval would consist of a 95% lower confidence limit for the linear combination given here. Now, I just want to point out that with this linear combination, this is actually the negative of the one we used above. But I'm doing this because to keep the values positive, it just makes it a little bit easier to interpret what this means. Okay, but it's equivalent to doing it the other way as well. So using this linear combination, the lower confidence limit, the 95% lower confidence limit for this linear combination, it turns out to be 99.754. And so we can say that we are 95% confident that the mean yield of variety 4 is at least 99.754 pounds per acre greater than the mean of the mean yields of the other 3 varieties. All right, let me say that again. We are 95% confident that the mean yield of variety 4 is at least 99.754 pounds per acre greater than the mean of the yield means of the other 3 varieties. Now, if we had taken the linear combination as we expressed it above, which would essentially be multiplying this linear combination by -1, then instead of constructing a lower confidence limit, we would have constructed a 95% upper confidence limit. All right, and so then that lower confidence, or the upper confidence limit, would be a negative 99.754. And so then we could interpret that value based on that corresponding linear combination. But again, it's a little bit, it's not quite as clear, all right, but it would be the exact same interpretation. All right, so let's move on. So as an additional exercise, what I want you to do is to perform the following analyses. Perform all pairwise comparisons between variety yield means. Perform each pairwise comparison at the 0.05 level of significance, and then construct 95% two-sided confidence intervals for the difference between each pair of means. I'm going to suggest that you do another example. I'm not going to work it out here in these notes, but this is more of an exercise for you to do. What I want you to do is to consider again the experiment to compare the 5 lentil varieties that we described and analyzed back in example 2.3. We did the analysis of variance for that experiment in example 2.3. And so now we're going to use the procedures presented in this section to do the following follow-up analyses. In particular, perform all pairwise comparisons between lentil variety yield means. Perform each pairwise comparison at the 0.05 level of significance. Now there are 5 varieties, and so there are going to be 10 pairwise comparisons. And in addition to that, remember that we don't just test hypotheses, we always want to construct the appropriate corresponding type of confidence interval. And since we are, these are pairwise comparisons, which are expressed in terms of a difference between pairs of means, what we would do then is construct 95% two-sided confidence intervals for the difference between each pair of means. So do that just to get some practice on using the techniques and procedures that we've been discussing in the last couple of lecture videos.